In this video, we're going to talk about box plots. Box plots are a nice way to display quantitative data. The following data is the commute distances, that in miles, of 22 students in a face-to-face section of Math 153. You can see them below. The first step in creating a box plot is finding the 5-number summary. Take a moment and find the 5-number summary. Pause this video and see if you can be successful in doing it. The 5-number summary, as you remember, consists of the minimum, the first quartile, the median, the third quartile, and the maximum. Let's find the numbers. The minimum and maximum are pretty easy to find in our data set because our data set is already sorted from the smallest commute distance to the longest one. So our minimum value would be 1 mile and our maximum value would be 35 miles. Next, we want to find the median, the middle position of the data. Here's a nice shortcut to help you along with finding the median. The position of the median can always be found by taking n plus 1 and dividing it by 2. Again, we have 22 values in our data set. Add 1 and then half that sum, you end up with the value 11.5. Now what this is telling us is the position of the median. So our median is located between the 11th and 12th value in our data set. So if you count over to find between the 11th and 12th, you will notice that it occurs right here between the last 6 and 8. Now it's not an actual value in our data set, so we're going to have to find the midpoint between these two numbers. Now it's pretty easy to do when it's 6 and then 8. Most of us agree that 7's halfway between, but sometimes the numbers aren't spaced out as nicely. So this little ability to add the two values and then half them will give you the midpoint between 6 and 8, or any two numbers you're working with. Therefore, our median is 7. The third and first quartiles are found by essentially finding the median of the first half of the data, and then again finding another median or midway point in the second half of the data. So if we take a look here and count in, we will notice that our middle of these values right here, these 11 values, falls right on this second 4. That's our first quartile. Again, if we find the midpoint or the median of this, you'll notice that it falls on the 12, the first 12. And that is our third quartile. So these are the 5 numbers we're going to use, along with a couple of other things, to make a box plot. Next, we'd like to determine if there are any outliers in the data. First, we're going to need to compute the IQR, short for interquartile range. If you recall, the interquartile range is Q3 minus Q1. So for our problem, that would be 12 minus 4, which is 8. So our interquartile range is 8 miles. The middle 50% of our data, or our students, commute distances only differed by 8 miles from one another. We're going to use this interquartile range to compute what's called a lower fence. Lower fence is 1.5 interquartile ranges below the first quartile. So if we plug in what we know, 4 for Q1, 8 for our interquartile range, and do the math following the order of operations, we'll discover that our lower fence is -8, which doesn't make too much sense in our data since these are miles, and miles and distance isn't necessarily recorded in negative numbers. But we go ahead and still compute it just to see what that value might be. In different situations with different data, our lower fence often will come up with a value that's valid. Our upper fence, and again, because of this negative value, none of our data was outside the lower fence. Our upper fence is 1.5 interquartile ranges, this right here, above the third quartile. So if we plug in the 12 for our third quartile, and again the 8 for the interquartile range, and do the arithmetic, we discover that our upper fence is 24. Now, if you recall, we had many values in our data set, I wouldn't say many, a few, that were above 24. And that's what these fences are doing. They're saying these are boundaries, and if any values in your data set fall outside the fences, then they're considered legitimate outliers in the data. 3 of our values are outside of the upper fence. Thus, 25, 30, and 35 are going to be considered outliers in our data. And the box plot we create will feature this fact of the outliers. So let's get to making this box plot. So what I've done here is just provide an axis for us to work with that jumps by increments of 5 miles. So the box is the first thing we create. The box is comprised of Q1, there it is at 4, a long horizontal line there at Q1, a similar line at Q3, and then so this is essentially the bottom of our box, the lower end, and this is the upper end of our box. Just making some vertical lines to make it a legitimate box here. Oops. And you can see here that the distance here between the first quartile and the third quartile, that physical distance you can see, is our interquartile range. Another horizontal bar that goes into our box is the median, and it's 7, so it goes in right here. So this is the box of the box plot. The next thing I want to do is to plot the outliers we found. We found outliers at 35, 30, and 25. So they're going to go in as sort of a dot or an asterisk or a triangle. Different softwares use different little symbols, but they're definitely a distinctive symbol that is used in the box plot. And what else makes this special is that these dots are not connected to the whiskers. You might have heard that in high school or another math called a box and whisker plot. They're not going to be a part of these extensions that are going to come from the box. So we connect out up to the whisker here to the next highest value in the data set. So if you look in the data set, the value that's the next highest compared to 25 is 17. So that is why this whisker only extends to the value 17. So it kind of gives us another bit of information. It is saying, hey, we've got these sort of extraordinary commute distances with respect to the rest of the data, and the next highest one is only at 17 miles. And again, now we're going to make the lower whisker, which will extend down to, in this case, our minimum of 1 mile. So here is our box plot. It's a nice, again, graph for quantitative data. It has a neat feature that it shows the outliers, if there are any outliers in your data set. And the absence of these symbols means, no outliers. So if those 3 students hadn't reported or weren't in my class, then we would not have this feature up in the top of the graph. It would just be this down here. But they were, and they did report them, so we're showing them as significantly different or than the rest of the group. One last thing to mention about a box plot is one of the general purposes of it, and that is to show us visually the 4 quarters of the data. And that means that we're dividing the data values into 4 equal parts. So essentially 25% of the data is above the third quartile, the top of the box. So you can see here, this is 25% of the students, around 5 or so of them. And these are, you can see that their commute distances differ from as down here at 12, that was our third quartile, up to as high as 35. So there's a lot of variability in the commute distances in this top 25% of the data. The second 25% of our data is located between the median and the third quartile. So again, not as much variability as we can see here. You can just see that the distance between the line in the middle and the top of the box is a lot smaller than the distance of the top features of the graph. Another 25% of the data, again, just as many students are right here, but you can see that their commute distances are very similar to one another. And finally, 25% of the data is below Q1, which was 4 miles. So 25% of our students in the class had a commute distance of 4 miles or less. So that's a lot of what a box plot is telling us, is it divides the data into 4 equal parts as far as the number of data values in each of these features. But as you can see, the way they are spread out has to deal with the actual values that the data takes on. So it's just nice to keep that in mind when you're interpreting a box plot.